Welcome back to the next video, everybody. Today's video is on the order of a finite flat group scheme. So in this section, S will be a locally Noetherian-based scheme. So it's covered by Noetherian schemes locally. And we'll define an S scheme X to be finite and flat over S if the structure sheaf OX on X is locally free of finite rank as an OS module. In other words, if and only if there's a covering of S by affine opens, let's say U equals spec R, such that pi inverse of U is spec A, where A is a finite rank R module. And what's pi here? Pi is just the map from X to S. It's the structure morphism given by the fact that X is an S scheme, okay? Just note this isn't really the generic definition of finite flat from algebraic geometry, but it's equivalent to it in our specific setup. And it's, I think, personally a little bit easier to think about than the generic definition. But you should see Vakil's notes, chapter 24 for more generic information. It also turns out that this rank here, A is finite rank as an R module. That rank N is locally constant on S, and it takes on non-negative integer values. And so, for example, if S is connected, the rank is just constant, right? And so we call this N the order of X over S. And you can see, again, Vakil's notes 24.4 for more information about this, or Hartshorn, or whatever you like. Okay, we'll denote the order of X over S by this kind of index notation. And so when I write something like bracket XS equals N, I mean X is finite and flat over S. So that's just buried in the notation of order N, of course, okay? So the first thing you should wonder is, what are the basic properties of order? Does it play nice? Does it have the properties you expect? And the answer is yes, by and large. So first of all, let's say I have two morphisms of schemes, one from X to Y and one from Y to S. Let's say the order of X over Y is a positive integer M and that it's constant. Okay, then X is finite flat over S if and only if Y is finite flat over S. And then in that case, when that happens, the order of X over S is the order of X over Y times the order of Y over S, much like you'd probably expect, right? Okay, what else? If the order of Xi over S is Ni, where I is equal to 1 or 2, then what's the order of the product of the schemes X1 cross X2 over S? It's the product of the orders, just like you might expect. It's N1 times N2. And then finally, order behaves well with respect to base change. So if the order of X over S is N, then the order of the base change of X to T over T is N for every S scheme T. And so again, the picture there is like I've got this map from X to S, the structure map. I've got another S scheme T, and then I base change X over to T. And this order is N, so this order is N as well. And for proofs of all this, you can see CSS, page 133. I'll give two real quick examples here, I suppose, or I guess really one example. Our main concern for this chapter, chapter 5 of my notes, is finite flat S group schemes. But our only examples so far, and the ones in the group scheme examples we've covered, are the constant group schemes S sub S attached to a finite group X. And then of course their duals D of X sub S, where X is abelian. And it's easy to check that in both of these examples, the order is constant, and it's the same as the order of the group X, the usual group theoretic or set theoretic order. And so in particular, if N is a natural number, Z mod NZS and mu sub NS, so the constant Z mod NZ group scheme and the constant nth roots of unity group scheme, those both have order N, because Z mod NZ and mu sub N as groups have order N. And so that's nice to know. So order not only behaves well kind of property wise, but the word order actually makes sense as a definition here. And then we'll give one last slide here. Let's specify, what are we going to be doing with all this? Well, if S equals spec R is affine, say, then any finite flat S scheme is also affine. So that's a great thing to know. That makes things easier. We can always study locally then. And the case we're going to be looking at is when R is the ring of integers in a local field, p-adic numbers or a finite extension or something like that. And in particular, the case we'll be looking at most is when R is just ZP, the p-adic integers. And so we can assume that G equals spec A is affine this entire time when we're dealing with a finite flat S group scheme G, because of this discussion up here. And we'll also assume that A is free over R and not just locally free. Now that's not clear why you can do that, but you should be aware of the fact that freeness is automatic from local freeness when R is a local ring, which ZP is. And this is covered in Vakil's notes in 24.4 again. So this is not totally obvious, although it's not too hard either. Let's also finally note that if the order of G over S, which we might also just write as the order of A over R, because everything's affine, S is spec R and G is spec A. So if that order is N, then the augmentation ideal is locally free of rank N minus 1 as an R module, essentially because A breaks down into like a copy of R plus I, remember from the last video. And so the upshot is when N is 2, our job is just easier. When N is 2, I mean, we have the augmentation ideal is just a rank 1 R module. It's just isomorphic to R's modules. So things should be easier there. All right, more on this stuff next video. So thanks for watching, and I'll see you then.